minus del square phi by del x del y. Okay. So we started with these, and now, so before we go to the derivation of what Irwin expression is, so a lot of names are there. Like we started with Griffith, and then we jumped to Irwin, but the contribution of English is also there before what Griffith did. And we also have other people like Westergaard, Airy function. And Westergaard function, one of his function we will use for derivation of Irwin's expression. And apart from Westergaard has given a lot of stress function, which are based on the same idea that what you have to satisfy is the equilibrium of stresses, and then you have the strain compatibility equations, which I showed you in the last class for 2 dimension, and for 3 dimension it can be written as of whatever function you have is equal to 0. Okay, so this expression simply means del to the power 4 phi by del x4 plus 2 into del 4 by del 2x del 2y plus del 4 phi by del y1. So del 4y is equal to 0. So this is equal to that. So this is what every function, and this is strain compatibility equation, which the physical essence of that I told you in the last class. And this is also biharmonic function. Okay. So this, any phi has to satisfy this. Okay, and if that satisfies, then using these equations we can find out the expressions for stresses. Once we have stresses, we can find out strain. Okay, so before we go there, there are certain things which we need to know. So one is an analytic function, and analytic function, the definition is that the function is differentiable by whatever route you come to that point, and also in the neighboring point it is differentiable. The other way of saying it is that the Taylor series of that function will converge to that point. Okay, so if you have a function described by capital Z, then Z is differentiable at Z0, which is a point, which is a regular point, and it is also differentiable at the neighboring points. And when that is true, it is an analytic function. That's the definition of it. Okay, and then there are certain consistency which has to be maintained if we take an analytic function to be a complex number function. Okay, there can be real functions which are so not complex functions, which can be analytic function, but in stress derivation usually we take complex function, complex number function. Okay, and complex number function, if you remember, then this is described as x plus iy. Okay, and this is a small z, so I will try to write it like this so that we don't get confused with a capital Z, which is a function, and small z is just the expression of complex number in Argand plane. Okay, so there are some notations with complex number which we are not going to use, so we'll describe that. So usually in complex number, when we write z bar, then that simply means the conjugate of this. But we will define a z bar in a different way, so we shouldn't get confused with this. Okay? This is the usual notification in complex number. Complex number has shown a lot of benefits in many physical derivations. Although it has an imaginary part, but sometimes that imaginary part goes away. And the other benefit of this is that you can express it in the form of this way also, and that gives you a lot of benefit, because then you can, if you want to expand it using Taylor series, you can do that. If you want to have trigonometry associated with it, you can do that. Polar coordinate, you can do that. So a lot of advantages are there. Okay. So let us say that we have a function z, which has a real part and which has an imaginary part. Okay. And now let us find out. So let us say that z is real. When z is real, we want to find out the differentiation of this. Okay. So because it is real, I can write it as limit delta x tending to 0 u of x plus delta x y plus I b x plus delta x y delta. Okay. So this, because it is real, delta x is tending to 0. Okay. So this is simply del u by del x plus I del v by del x.
Okay.
Right? This is happening because z is real.
Sir, if z is real, then why there is imaginary part?
We are not initially ignoring it because we have a function of x in v also. So we don't know that it will come real or not. You can have some I somewhere so that it becomes I square, so then that will become real. So we don't know that. Okay. Similarly, now if we imagine z to be imaginary and do the same exercise, it is like mana x barabar ye, so then we come to the conclusion. So if z is imaginary and then we try to find out this, then what we will have, u x comma y plus delta y, and now we have to put I delta y here and limit of delta y tending to 0, plus we have I b, and you will see here how imaginary becomes real in this case. So v x y plus delta y I delta y. Okay. So the first term is what? I. So we have to multiply now I square by I square from the numerator and denominator. So I square will be minus 1. Right? Can we do that? I square will be minus 1 and I cube will be what? Minus?
Minus I.
So then we are not getting it.
So we will multiply and divide by
I. Okay, fine. So if we, yeah, that will work. So if we multiply this with I by I, then we will get I del u by del y, right? Because this will become minus, so I will have a negative sign, and then I don't need to do anything here, so this becomes del v by del y. Okay, so you see imaginary has become real now, the y part. Okay, so both of them we are coming to the derivative of this function z from two different approaches, and because it is an analytic function, these two must be equal. That's the definition of it. Okay, so that brings us to what? That this part, the real part, must be equal to the real part of this thing, right? So what do we come to is that del u by del x must be equal to del v by del y, and this is equal to what? This is equal to d of real part of z by d z. Can we say that? Or we don't have to write this. We can just write dz by z, right? And then this part will be equal to that part. So del v by del x will be equal to negative of. So del v by del x will be equal to negative of del v by del y
Del U.
del u by del y will be equal to dz. Okay. So these are called what? This have a specific name.
Cauchy-Riemann equation.
Yes. Yes. Okay. So if we need to write it in the form of the function z, then I can write it as del of real part of z by del x will be equal to del of imaginary part of z by del y, and that will be equal to del of real part of z by del z. The first one. And then the lower one I can write as del of imaginary part of z by del x will be equal to del of real part of z by del y, and that will be equal to del of imaginary part of z by del z. And we need these once we try to satisfy the biharmonic function. Okay. So Westergaard gives a lot of functions, and one of those functions is, he describes phi is equal to real part of this plus imaginary part. So y into imaginary part of z bar. Okay. So let me just check. Yes, this is correct. And what are these notations that I have to tell you? So z dash is simply this, right? And how many number of bars, or not bar, dash I put, it becomes that order of derivative. Okay, so z double dash will be d2 d by d square and so on. Z bar is integration of zt, and z double bar is double integration and so on. Okay, so these are not conjugate. Okay, so this is my function and I have to satisfy this. So what do I need to do? I need to find out the terms which are there. So del 4 phi by del x4. That is what I have to find out. So let us do that. So first I will find out del phi by del x, if that is phi. So del phi by del x will be simply real part of z bar plus y into imaginary part of z. Okay. Then I find the double derivative, and you should also try to do that while I am doing it. So then this will be real part of z plus y into imaginary part of z dash, and then I have, del 3 phi by del x cube, and that will be real part of z dash, or not z dash, z dash
plus
y imaginary part of
z double dash.
z double dash, and then I found the last term, which is real part of z double dash plus y imaginary part of z triple dash. Okay, अभी दूसरा करेंगे. del to the power 4 phi by del y to del 4 y. Do it. So del phi will be equal to del of del y, the real part of z r plus. Now here we have a problem because we have y also. Okay. So we will have y del of del y of imaginary part of z plus imaginary part
Okay,
of. Do we have z? Yeah. Z. Yes. So what is del y of real part of z is here. Del y of real part of z is will be equal to negative of del z of imaginary part of z, right? So this will be negative, and then del z of imaginary part of z bar will be what? Z simply, right? So that will be negative of imaginary part of z. Do you follow? तो करोगे तो पता चलेगा. करो. See del y of real part of z. Now we have to use CR. So del y of real part of z is equal to this, right? So that is negative of del z of imaginary part of z. Instead of z we have z bar. Okay. So z bar का differentiation क्या होगा? Z होगा. So then we'll have imaginary part of z, right? Okay. So first term is this. Then we have y, and del y of imaginary part of z is what? This is equal to real part of z. Okay. So y real part of z, and then we have. So we don't need to do anything here. So this is imaginary part of z. So this cancels out, and this is equal to that. क्या हुआ? Which dash?
Second term real part of z dash.
Second term, this one will be real part of z dash. Why?
Yes. So because this is the differential.
Yeah. So del y of imaginary part, but we really have what? Oh, we have z. Okay.
Yes. Dash आएगा.
So del y of real part of z bar is what?
Imaginary part of z. First one is correct. Second one.
So what do we have? Real part of z plus imaginary. No. This is wrong.
Okay.
I have to use this function, not this function. I have used delta 5 at x. So del y of real part of z double bar,
Yes.
and then y into imaginary part of z bar. So now this will become what? Z bar, right?
Yes.
And क्या हुआ?
Last one is z.
Imaginary part of z bar.
Z bar.
And this will become
Z
this,
bar.
and y
No, it's
real part of
z.
z I will have, right?
Yes, sir. Yes.
So now this is okay, right?
Yes.
So this will be this.
Z bar.
Z bar.
So now it is cancelling out.
Okay.
So you will have this.
Okay.
Okay. Now you find out, because you have now learned and finding out mistakes.
Del two.
So find out this second derivative, then third, then fourth. So I need this. So I will have to keep it somewhere. So I will write here 4 5 by 26 to the power 4 will be equal to real part of
Z double dash plus y imaginary part of Z triple dash.
imaginary part of z triple dash. Okay. So this I don't need now. So did you get del 2 phi by del square y. What is that?
Real part of z minus
Real part of z minus
y imaginary part of z dash.
z dash. Okay. All of you are getting that?
Yes.
Okay. So then, have you found out the third derivative also?
Real part of z dash minus
Real part of z double dash.
This one? Then real part of
z dash
z double dash plus
इतना ही z.
बस इतना ही है?
Means sir, minus of y real part of z double dash
Minus of y real part of z double dash
minus twice imaginary part of z dash.
z dash. Okay, I am not checking it. This is the final expression. Okay, is that what you are getting? All of you are getting? The second derivative is correct? Okay, so let us proceed from there. So if I want to do the derivative of that, so that will be del of real part of z divided by del y minus y imaginary z dash and del y minus minus imaginary z dash. Okay, so this will be equal to, not this, but the third derivative will be equal to that. Okay. So what is del y of real part of z is negative of del z of imaginary part of z, right? So derivative of z is z dash, right? So imaginary z dash, negative of that we will get, right? The negative of imaginary z dash, and then we have negative of y, and del y of imaginary part is there. So this will be equal to derivative of real part of z. So z dash, so z double dash, right? So z double dash, so real part of z double dash minus imaginary part of z dash. This is what we'll get. So negative will be twice of that. We'll get twice of imaginary part of z dash minus y real part of z dash. So this is correct. So tell me this also.
So y real part of z triple dash
Y real part of z triple dash
minus 3 real part of z double dash.
That's it.
Sorry.
So y imaginary
part of z
triple dash.
Y imaginary part of
triple dash.
okay.
Minus 3 into same.
This is okay.
Yes.
Any one of you are getting this? यहाँ तक तो पहुँच गए. इसका इंटीग्रेशन करेंगे तो यहाँ आएंगे. You are getting it? This is the same expression you are getting? Okay. अब एक और बचा है.
It's fine.
Yes. But that you can do because we have the double derivative somewhere, no? If you have written it somewhere. So we need to find del to the power 4 phi by del x square. This, okay? 4. So you can start from del 2 phi by del 2 x, and then you do the derivative of that with respect to y once and twice, and then you will get it. So start from here. What was the expression for this?
Real part of z.
इसका
Real part of z plus 1
Plus?
times imaginary part of z dash.
Okay. So now you have to do del 3 phi by this del y. So that will be del y of real part of c plus y del imaginary part of z dash del y plus imaginary part of z dash. Okay. So del y of real part of this is negative of del z of imaginary part. So that is, ये कौन सा term है? Here, ना?
Yes.
So this will be negative of z dash, right?
Yes.
So this is negative of real part of z dash. Real part of imaginary part.
Imaginary part.
Negative of imaginary part of z dash. Okay. So this we have done. Plus now del y of imaginary part of this thing is equal to real part का derivative with respect to z.
Real part
Right?
of z double
So
dash.
z double dash. Real part of z double dash. So y into real part of z double dash plus imaginary part of z dash. Okay, so ये cancel हो रहा है.
Yes.
So then we are getting what? Y real part of z double dash. अभी इसका final expression we need. So del 4 phi by this will be del y of y real part of z double dash. Have you done this?
Yes. So
What is the final expression?
real part of z double dash
Real part of z double dash
minus y
minus y
imaginary part of z triple dash.
imaginary part of z triple dash. This is it? Okay. So I hope here I don't have anything, and now I don't need CR, so I will wipe it out. Okay, and now we just need to plug the values. So del 4 phi by del x to the power 4s real part of z double dash plus y imaginary part of
Z triple S.
z triple dash plus 2 into, I need this thing, so that is real part of z double dash minus y imaginary part of z triple dash, and what else? I need this one.
Yes.
So this is y imaginary part of z triple dash minus 3 into real part of z double dash. अभी इसको खोल देना पड़ेगा. So ये ऐड हो जाएगा and इससे कैंसिल हो जाएगा. है ना? So this is gone. This is gone. This is gone. So what remains is 2 into triple dash plus this. So I will have single in negative, right? So I will have single in negative and this will be gone, right? ये भी cancel हो गया.
0.
Oh, so then we have proved it.
Proof.
Okay, that biharmonic function is satisfied with this function. Okay. Good. Now we need to apply the boundary conditions. Okay. In presence of a crack. So for that, what the derivation of George Irwin takes a plate which is infinite and you have a crack inside, and then you have stresses. And there is some confusion in the literature that the derivation of Irwin was for uniaxial condition or biaxial condition. Okay, but later on people corrected and found that it must be for biaxial condition. It cannot be for uniaxial condition. So you have stresses here also and here also. Okay, and you have the origin here, so this is your r vector and this is your theta, and this length is a and also a on the other side. Okay, so apart from fulfilling the biharmonic, so strain compatibility relation, this must also satisfy the boundary conditions which we have on the graph. And what are those boundary conditions? So when the point is between the tips, so any value of x from minus a to plus a, in that range, what do you have? So minus a to plus a.
सर इसके
Yeah.
सर वो लेटरल डायरेक्शन में जो स्ट्रेस लिए सिग्मा वो इसलिए लिए क्योंकि स्ट्रेन आ रहा है लॉन्गिट्यूडिनल डायरेक्शन में मतलब यूनी एक्सियल
No, it is not mu into sigma. It is not uniaxial.
नो नो सर यूनी एक्सियल के बजाय बाई एक्सियल कंसंट्रेशन क्यों किया सर ये पूछ रहा हूँ मैं
So it appears that the function and these relationship can only hold true if you apply a boundary condition for biaxial condition.
सर तो जो स्ट्रेस है इस डायरेक्शन में
हाँ.
उसकी वजह से जो स्ट्रेन आ रहा है इस डायरेक्शन में इसलिए उसको लिया गया
That I'm not so sure of. Because so far whatever we have assumed is this. So this is a biaxial condition of stress. This is for plane stress. We don't have sigma GZ here. So it's not triaxial, it's biaxial. It's also not uniaxial. Right? So we have a value of sigma xx. It will be a special case when we put sigma xx is equal to 0. That will be a special case, and I do not know. We'll have to put sigma xx is equal to 0, and then we'll have to see if these equations hold or not. Okay, so if sigma xx is equal to 0, then this should be 0. And if you cannot say that this is 0, then it must be for biaxial condition, the derivation. Okay, so you can find out del 2 phi by del y square with this, and then so do we have del 2 phi by del y square? So what is it?
रियल पार्ट ऑफ z माइनस y इमेजिनरी पार्ट ऑफ z
Real part of
z
minus
y इमेजिनरी पार्ट ऑफ z
z dash.
yes
So this must be 0. So that means real part of z must be equal to y into imaginary part of z dash, right? So what is it? I have wiped out CR equation. So imaginary part of c dash is, it means what? So this is imaginary part of, so this is del of imaginary part of c by del c. Okay? And real part of z is real part of z. So if it is equal, is this equal? Will it be equal? Can we say, is there a proof that it will be equal? There is no condition which says that this will be equal, right? So that will be a special case, and if this becomes equal to z, so if this is equal to that, so y cannot be 0, right? Y must be finite because that's an axis, right? So then what should we say? What can we say? How can we say that this minus this is equal to 0? How can we say that? If y is finite and it can take any value, then this part must be equal to 1 by y of this part, right? And that becomes a special case. And once we do that, once we say that this is happening, then we'll have to plug in this info everywhere in the further derivation. You can do this exercise and see if it works or not. Okay. Fine. So the boundary conditions for in this range, so that means for all the x's in this range, okay, and for y is equal to 0, so that means along the major axis of this ellipse, what do we have? What stress will be 0 for sure along that line, along this line from here to there. So we cannot have stress on the surface, right? So along that line sigma y must be 0, right? We cannot have also shear stress. Okay. Then when z is infinity, that means in far field, means far away from the influence of the crack. Far away from the influence of the crack, the stresses which are there must be equal to the applied stress, because they will not feel the crack, right?
This means at the boundary.
No, so it's an infinite plate. It's an infinite plate. Okay? So this goes to infinity. The width of the specimen goes to infinity. There is no dimension to that. Okay? So far away means what? What is the meaning of far field? Far field is when you don't have the influence of crack. इतना दूर है कि फर्क ही नहीं पड़ रहा. Okay? So when that happens, then you will have all the stresses must be equal to the applied stress. Okay? And along the line you will have shear stress equals to 0. So when you don't have crack, then there will be no shearing. Okay? This is the second boundary condition. And the third boundary condition is along y is equal to 0 for any value of x. So along y is equal to 0 for any value of x, what must be satisfied is that shear stress will be 0. These are the three boundary conditions which must be satisfied.
So in the second boundary condition,
Yeah.
when we study about plane stress condition, there are shear stress. Then why
Yeah.
we are considering 0?
Far field. It is at far field when z is infinity. When z is infinite. Far away from the stress, you should have shear stress is equal to 0. That should be the boundary condition.
From applied load will not be applied
Load will not be applied.
at that in x.
Yeah.
Shear stress.
Why load will not be? What?
So load is
Sir,
there.
plane stress condition
Shear
में
stress.
shear stress 0 कैसे होता है? प्लेन स्ट्रेस कंडीशन में मानते हैं सिग्मा x में डायल y में.
Yes.
लाइक प्लेन में निकाल दो shear stress होता है.
So when you have sigma xs is equal to sigma yy, then what will be the value of shear stress?
0. That will be the midpoint of the Morse.
So with these boundary conditions, a function was given by Westergaard, and that function is sigma c by square root of b square minus a square. Okay? So this function was given by Westergaard. There are a lot of functions given by Westergaard. One of the function is this. And this small z is this c. So this means x plus iy. And this will satisfy all the boundary conditions. That you can check. Okay? So now what do we do? Should we try to satisfy the boundary conditions? Or you try to satisfy the boundary conditions? in your tutorial with this function. Those are the boundary conditions, and you need to satisfy using this equation. Okay, how much time do we have? Okay. Then, after doing all those things,
Satisfied.
at the end, what Irwin does is that he shifts the origin from here to the tip of the crack. Okay? So that means Z becomes Z0 plus A. And then the function becomes sigma, Z0 plus A square root of Z square minus A square. Okay? And if the crack is too long, then we can do what we usually do. We ignore Z0. Okay? So then we'll have sigma A divided by square root of what will we have? So this will be Z0 plus A whole square. So what will we have? Z0 square plus 2 Z0 A plus A square minus A square, right? यही होगा ना? So this is gone. This is because we have assumed this, so this will be ignorable, right? So then we will have the function is equal to sigma A divided by root over 2 Z0 A. So this I can write as sigma root A divided by root over 2 Z0, or I can write it as R e to the power I theta to the power minus half. Right? Now we have Z. Now we need to use these to find out sigma xx, sigma yy, and sigma xy. Okay? So if you want, you can do this as an exercise, or we can do it in the next class. But what you can see here is that we are approaching now. If those of you who know the expression of stress at crack tip, you must be able to see it. Okay? That we are approaching there. And so I will tell you the secret. So the expression for sigma xx and sigma yy and sigma xy are sigma root A, so sigma root over 2 pi r, and you have root A also, and then f of theta. Okay, and you will get this similar thing, but f theta will change. F theta will change, and you will have these kind of expressions. Okay, I think there is a mistake. This will be that. Okay, and then Irwin has defined it by putting a pi inside, and then for no reason he makes it like this, and it becomes this. So what do you see is that in all the expression of stresses, you have this thing common, right? For sigma xx also, sigma yy also, and sigma xy also, right? And this defines that when r tends to 0, all of the stresses will become infinite, whatever is the value of f theta. Okay? This is described as by the symbol K, okay, and called stress intensity factor, and this is credited to George Irwin. And there is a group of fracture mechanics people who believe that there was no need of pi. Appears to be true. And they say that if you didn't have pi, even then, whole of the fracture mechanics would have been same. It's a constant value, so there was no need of it. But because Irwin did it in this way, people have been using it. And this signal was already there in 1921 in Griffith's expression. So what was Griffith's expression? G was equal to sigma pi square A by E, right? So sigma is square pi, not pi. Sigma is square, right? So if I write the expression, so G, when it reaches a critical value, I can take this and take a square root of that. So that will be equal to what? Sigma root pi A. E is elastic modulus, and G, when it reaches the critical value, it becomes GC. So that is also a material property, right? So this becomes a constant value. That means this is describing the critical value. So this signal was already there in the expression of Griffith, but it took 20 years for somebody to arrive at this equation. Okay? So we'll do this in the next class, finding out the expression of sigma xx, sigma yy, and sigma xy. Although there is a part missing, that the same equations could be derived via different routes, and one of them was using a Taylor series. We will not do that derivation, but that was done independently by William, okay, I think in 1970s. Okay, and he comes up at the same expression, but the difference is that all the stresses also have higher order terms of R. Okay, so the first term matches with George Irwin, root R, but then you have higher order of R and derivative of the function. Okay, and that contributes to fracture mechanics later on. We will see that there is a term in the expansion of stresses. So in these equations, there is a term where it's a function of R, simply R, not root R. So when R tends to 0, that function tends to 0, but as soon as R has a finite value, that function has a finite value, and that describes the constraint on the crack tip. It's called T stress. Okay, so you will see that there are different parameters of fracture mechanics, like J integral was derived by James Rice, right? So that's why it is J. Griffith derived and named it G. But George Irwin is deriving something and he is naming it K. Why? Why not I or why not G? George Irwin. Why K? There is a story in, it's a different story, but the story is people were not very happy in Princeton with Professor John Nash, because John Nash was not very friendly guy. Okay, so one in the movie A Beautiful Mind, you will see a scene where he goes to the class. He is not in a mood to teach because he thinks it's a waste of time. Sometimes we all think that. And he goes to the class, he writes 3 problems and says that it will take full semester for some of you and a whole life for most of you. And if you can solve it, then we will take another class, and he throws the books in the dustbin and he says that we are not going to follow it. So the colleagues of John Nash were not very happy with him. And one of them, so you see the contrast, one of them wrote a paper, the colleague of John Nash, he wrote a paper, a research article, and gave a co-authorship to John Nash. People asked him in an interview, and that interview is on YouTube, people asked him that why have you given the co-authorship, because he has not collaborated with you. So he says that I couldn't solve this mathematical problem and I tried a lot. And one day in my dream, I saw that John Nash is telling me the solution. So in his dream, the solution came from him only. But it came through John Nash as a character in his dream, and he gave the contribution to him in his research article. And similarly, George Irwin has given this K symbol as a contribution to his colleague Keys. And that's why this symbol is there and it has become immortal. Okay, so we end this class today.